So the live fuel moisture model in the 7888 has always been acknowledged to be the weakest submodel in the system. The original developers never actually intended for that model to last very long. Though they intended for new science to be developed to be able to replace that at the earliest possible convenience. And 40 years later, we're still using the original one. So what we find is that we can do better. So the new herbaceous and woody fuel moisture calculations are using the growing season index. And basically we use that growing season index and make a couple of assumptions about when green up happens along that the index continuum, and how to transform it between the index and actual fuel moisture values, and use those numbers to drive our new fire danger calculations. The growing season index is just a meteorologically based phenology model, meaning that we take weather conditions, combine them together into an index, and that index relates to phenological conditions, basically observable conditions of plants, things like a transition from dormancy to green up, or a transition from green up to full canopy development, or from full canopy development to transition to dormancy, or as herbaceous fuels green up and reach peak greenness and begin to cure. We see both of those events, both for woody and herbaceous fuels, from the same index. We see the events that are driving their change. The whole goal is to get rid of things like green up dates, curing dates, freeze and dormant dates, to create a system that predicts those things for us, so that we don't have to enter them into a system that can also predict them in the past. So when we're running a historical analysis, it can allow the green up date to vary from year to year, as it does in nature, more mechanistically. By switching to GSI, we get rid of things like climate class and the green up dates, season codes and greenness factors from the 88 model, and to lead us to a new way of looking at live fuel dynamics. The growing season index is calculated daily from 24-hour weather summaries. It has three inputs: minimum temperature, which is the 24-hour minimum temperature calculated from the hourly temperatures. The vapor pressure deficit, calculated, basically vapor pressure deficit is just a recalculation, or a similar calculation to relative humidity. So instead of calculating the actual vapor pressure to saturation vapor pressure as a ratio, the way that relative humidity does it, vapor pressure deficit just calculates it as a difference. And it's measured in units of pressure, which basically says what is the moisture deficit of a parcel of air in terms of the pressure of water vapor. Basically, that you can calculate VPD from maximum temperature or average temperature, and both Fire Family Plus and WIMS allow you to switch between using VPD max, which is a vapor pressure deficit calculated at maximum temperature, or VPD average, which is a vapor pressure deficit calculated at 24-hour average temperature. The last piece it uses is photoperiod. Photoperiod and day length are synonymous, but it basically just tells you how many hours of sunshine you have for a particular place on a given day. And that varies as a function of the latitude of a particular location and the day of the year. And it's easily calculated by a straightforward little function. The way that GSI works is that it's a collection of indicator functions. And an indicator function just goes from 0 to 1. This is mathematically very important, because even though it's simple, a value of 0, if you multiply 0 times any other value, you get 0. A value of 1, you multiply any other value and you get that value. So what we do is we define limits that say below a certain level, this particular variable is fully constraining plant function. So in this case, minimum temperature. When minimum temperature is below -2 degrees Celsius, which is somewhere around 28 degrees Fahrenheit, plants are completely unhappy. And as you increase above freezing, at some point temperature isn't limiting anymore. So in this case, as we get above 5 degrees Celsius, we assume that minimum temperature doesn't limit plant function any further. So the same works for photoperiod, that we know that through an examination of the literature that plants really respond in a range of about 11 to 12 hours for photoperiod. But below 10 hours is just not enough light for plants to be happy. So at any photoperiod below 10 hours would get an indicator value of 0, and any photoperiod above above 11 hours would get an indicator value of 1. And if you're in between 10 and 11, you get some proportion of value between 0 and 1. So 0.5 is halfway. So in this case, if you are at a photoperiod of 10.5 hours, 10 and a half hours, you'd get an indicator function value of 0.5. So we'll save that for for an example in a minute. But vapor pressure deficit's the only one that works in the opposite direction. Low vapor pressure deficits indicate a humid atmosphere, and high vapor pressure deficits indicate a dry atmosphere. So when we're below VPD of 900, we assume that a wet atmosphere means wet soils, and plants are very happy. As that VPD increases to 4100 pascals, once you get to that or exceed that, plants are fully constrained by water availability. So let's just do an example from this. And essentially, if we say that on a given day the minimum temperature was -3, and these are in Celsius, but they're easily converted. The photoperiod was, let's just say it was 11 hours. And the vapor pressure deficit was 800 pascals. If we look at how these functions work, we would say that we put this -3 into this function, and -3 is down here, which is below -2, which gives this indicator a functional value of 0. And even though our photoperiod is at 11, which would give this value 1.0, and a vapor pressure deficit indicator that was right here, which would give it a value of 1.0 as well. GSI is just calculated as the product or the multiplication of these three indicators. So in this case, it's 0 times 1 times 1, which is 0. In that respect, any time any one of these functions is below its lower limit or set to an indicator value of 0, you get a GSI of 0. The only way that you get a GSI of 1 is for all three of these constraints to be met. So if we keep the same example and we raise the temperature from -3 to 6, we can have a different example. So in this case, if the minimum temperature was 6, we go up here and we say that indicator function for now is 1.0, and the photo period was still 11, and the indicator value was 1.0, and the vapor pressure deficit was 800, which makes the indicator value 1.0. And if we multiply 1 times 1 times 1, we get a GSI of 1. Essentially, that's how this works, is that the only way you get a GSI of 1 is for minimum temperature to be high enough, photo period to be long enough, and vapor pressure deficit to be low enough to yield the conditions that make for happy plants. One of the things that we get is the ability to map it out across the planet to understand what limits phenology in different places, and we can see that in certain places phenology is heavily influenced by water availability. So these red areas in the Rocky Mountains, you can see these blue areas where they're limited by temperature. In the high latitudes, they're limited by both light and temperature. And in some places, particularly in the Andes and in the Tibetan Plateau, you can see areas that are purely temperature limited. And then in the tropics, you can see places where only photo period, and in some cases very little seasonality of weather. So you have year-round evergreen plants. The way we use this information to get live fuel moisture is we start out with our inputs, our temperature, minimum temperature, vapor pressure deficit, photo period, and we model the GSI along with some site parameters, and then we translate that GSI into a live fuel moisture value just by applying a simple scaling. If we look at some examples of weather, we can see how this works. So we can see that as we increase in minimum temperature, we reach a point where we get above that freezing threshold. And this area in between here really is the outer limits of the growing season. We also see periods of time during that, like in this example, late June and early July, or just right up to July, where vapor pressure deficits skyrocket. And the combination of those two things leads to an increase during the temperature limited season, and then a decrease during that vapor pressure deficit extreme period, and then a recovery that looks essentially like this. So we have an increase, reach a peak, trough when the plants get water stressed, recovery, and then a transition back to dormancy. So this is our green up threshold that we have to define for the model to work. So in this case, growing season index of 0.5 tells you that once you exceed 0.5, that the plants have greened up, and once you cross it on the downward side, plants have transitioned back to dormancy, or they're fully cured, depending on the type of plant. If we look at how do we interpret these things, as GSI goes from 0 to 0.5, we're in basically a pre-green condition. Still, plants are still dormant or coming out of dormancy, but they haven't greened up yet. So as the GSI exceeds 0.5, plants green up, and between about 0.75 to 1, plants reach their full canopy development. On the downward side, we see that as you drop from 1 to 0.5, we start to see curing in herbaceous vegetation. We start to see leaf senescence as you drop below 0.5, and then as you get from well below 0.5 and back to 0, you start reaching full dormancy. So essentially, the way we get to GSI fuel moistures is we calculate the GSI, we rescale it to a common scale, just using the calculated historical maximum, so that the GSI always goes to 0 to 1, and then we calculate live fuel moisture from that rescaled value. our limits of those indicator functions that I showed you before are defined here. So the lower limit is 28.4 degrees Fahrenheit or minus 2 degrees Celsius for the lower limit of minimum temperature, and then 41 degrees Fahrenheit or 5 degrees Celsius for the maximum of the minimum temperature indicator. Vapor pressure deficit is the low is 900 pascals up to 4100 pascals. So 900 pascals and below or smaller is where plants are fully happy, because it's a wet atmosphere and they're not losing a lot of water to the atmosphere, and it also is indicative of periods of a lot of water availability. And then once you get above this 4100 pascals, generally those are the times and places where it's very dry, there's not very much water available, plants are not very happy. 3600 seconds is 10 hours of photo period per day, and then 3960 seconds is 11 hours. So basically these sets of parameters define the upper and lower limits for those indicator functions that are used to calculate GSI. And the default maximum GSI gets calculated from the historical data, and then the only thing we have to do to make this work is define a green up threshold. So that green up threshold starts at we just use a default of 0.5. So as GSI is increasing in the springtime, when it crosses 0.5, we call it green up, and once it exceeds that point, that's when we start scaling the live fuel moistures. So we go for the live fuel moistures for the herbaceous fuels. The minimum fuel moisture we assume is 30%, and the maximum is 250%. For woody fuels, the minimum is 60% and a maximum of 200%. And those are consistent with the way that the 78 and 88 values were set to defaults before. So these are just the mathematical equations of the indicator functions themselves. So we have basically 3 indicator functions: an IVPD, an iPhoto, and an ITMEM. Those are, and when VPD is greater than the maximum defined in that list down here, you give it a value of 0. When it's less than or equal to the minimum, you give it a value of 1. And when it's in between, you scale it as continuously between 0 and 1. So if you use these equations to plug in the photo period, the minimum temperature, and vapor pressure deficit, you get 3 numbers out that are naturally bounded between 0 and 1, continuous, and those 3 numbers get multiplied together to give you GSI. The GSI, so this is just a summary of how we implement GSI slightly different for herbaceous and woody fuels, and that we assume that the green up threshold for both is 0.5, and if you don't have a reason for changing it, don't. And this is just the straightforward equation for how we derive woody or herbaceous live fuel moistures from GSI. Basically, it's a linear scalar that once you're above a green up threshold, it scales linearly between the minimum and maximum fuel moisture defined for that fuel type. So whether it's herbaceous or woody, so that when GSI is 1.0, for herbaceous fuels, the live fuel moisture is 250%, and for woody fuels, the live fuel moisture is 200%. And when the value of GSI is equal to the green up threshold, the live fuel moisture is at the minimum for that fuel type. So it would be at 30% for herbaceous fuels and 60% for woody fuels. And then it would increase or decrease linearly in between as the GSI increases or decreases above that green up threshold. And this is just an example of what that looks like. So out here in the on average, using a GSI of 0.5 as the green up threshold, The mean green up date happens about the later part of April, and we see an increase and a reach to some maximum fuel moisture just before July, and then on average things dry out in the summer, recover in the fall, and transition back to dormancy, and the end of the growing season happens about November 1st. And this is just an example of what it looks like compared to real data. So the red line is the measured live fuel moisture for sagebrush and chamise. Sagebrush on the left, chamise on the right. The blue line is the old model, which shows this really rapid green up that's not consistent with the observations, and it reached a peak several weeks earlier than the observations show, and then declines at a rate about consistent with what the others do. And then the GSI comparatively shows a similar rate of green up to the actual observations. Timing of the peak is the same time, and then a rate of decline that matches remarkably well. And there's also, so in WIMS, in the ENFDR screen, you can actually see the GSI parameters listed separately for the herbaceous fuels and for the woody fuels, so you can tab across. You can see the GSI parameters that we just talked about, -2 and 5 for the temperature, 900 and 4100 for vapor pressure deficit, and 3600 to 39600 for the photo period. And you can choose between using the maximum VPD or the average VPD. Set the running average length, because GSI is calculated every day, but smoothed with a running average, usually of 21 days. You can change the maximum GSI for scaling, so in places where the GSI doesn't get all the way up to 1, you can set it to the historical max GSI for a particular place, and it'll work better. And then you can define, or you can see the minimum maximum fuel moistures for herbaceous and woody.